Hey there, awesome physics students. Let's talk about mechanical potential energy and the whole idea behind it, where it comes from and why we use it. So we're going to start with the work energy theorem. That is, the net work done is equal to the change in kinetic energy, or the idea that work changes kinetic energy. And let's look at a particular scenario to start us off with. So imagine that you have a box on a ramp, and there's no friction here in any of these scenarios here. And what we want to do is, as the box slides down the ramp, we want to use the work energy theorem to predict how fast it's going. So to do that, we need to think about the forces acting on the box. So there's going to be the normal force acting on the box, perpendicular to the contact surface, and then the weight, which is mg, the force of gravity. And we notice that its velocity is down the ramp, and so if we look at that compared to the normal force, those two are always going to be perpendicular to each other. Since they're always perpendicular, that means the normal force is not going to do any work, and the only thing that does work is gravity. And so I only need to worry about gravity doing work. So if I imagine this thing going down a vertical height of y, I can write down the change in kinetic energy is equal to the work done by gravity. That's going to be the force of gravity times the part of the displacement that's parallel to gravity, which is just going to be that vertical displacement, y. Okay? All right, so that's nice. Let's try another more complicated scenario. Imagine there's a hill with some waves in it. And again, we're going down a vertical height of y from the top. So again, we need to think about the forces acting on this. So again, there's going to be the normal force acting, and gravity is going to point down the whole time. The direction of the normal force is going to change, though, as you go on this path, as it goes up and down and up and down. But notice that the velocity vector at every point is going to be tangent to the path, whereas the normal is going to be perpendicular to the path. So they will still always be perpendicular to each other, and the work done by the normal force will always be zero. So again, gravity is the only thing doing work, and so to write down the change in kinetic energy, I just need to write down the work done by gravity. That's going to be the force of gravity, again, just times this vertical displacement, because I just need to multiply the parts of the force and the displacement that are parallel. Okay, so let's think about one more scenario. Imagine I have a ball tied to a string, and a pendulum, basically, and it swings down to some lower point here. And the distance between those high point and the low point is y. Now again, let's think about the forces acting on this. So there's the force of tension acting along the rope, and then there's the weight, or the force of gravity, straight down. And again, I notice that as it moves, the velocity is going to be perpendicular to the rope the whole time. And so the tension is going to do zero work, because it's going to be perpendicular to the displacement the whole time. So again, the only force that's doing any work in this scenario is gravity. And again, I write the change in kinetic energy is equal to the force of gravity times the vertical only displacement, which is y. So after doing this a bunch of times, you see a pattern. I know what the answer is going to be every time if gravity is the only force doing work. So what I want to do is create a new thing called potential energy that will be associated with gravity that I can use. And the idea is that I want to write the change in energy is zero, or the change in potential energy plus the change in kinetic energy is zero. In order to do that, though, I need to start with this. So I know that the change in kinetic energy is equal to the work done by gravity, because gravity is the only thing doing work in this case. So to make this like that, I need to move this to the other side. And so it needs to become negative. So it becomes negative. The work done by gravity is negative, plus the change in kinetic energy will be zero. That means that this term here is that term. That is, the negative of the work done by gravity is the change in potential energy. So I'm defining potential energy to be the negative of the work done. Does that bother you? Well, let's think about why we would do such a thing. If we lift an object up, we want to say that the potential energy has increased, or change of potential energy is positive. But notice that the work done by gravity is negative, because gravity points down, but I'm moving this box up. So this WG variable inside the variable will be negative. So what I do is I put in negative out front, so a negative negative will make the whole thing positive. Okay. Another way of thinking about it is this negative sign means that potential energy is stored work. And the idea that the negative sign is the storing part. That is, with certain forces like gravity and the elastic force, I can do work against those forces, and then I can get that work back out later. I can store that work, and that term for stored work is potential energy. So gravitational potential energy, as you probably noticed through this, the equation that we can use for that is mgy. There's also another potential energy that we can use called elastic potential energy. That is, if we do work by compressing or stretching a spring, we can store that work and get it back out later. We'll talk about that one in a separate video.